Hello, and welcome to Section 7 of Virtual DAAG 2021. Our subject here is bridging between data and decision science. The data science has received a lot of attention at recent DAAGs and in the decision analysis community. It's a big source of change throughout business and industry. Our goal here is to help decision analysts understand the data scientists with whom they are asked to work. And we have three presentations here. Our first, we're looking at ethics and bias in the area of artificial intelligence. This is motivated by the DQ emphasis on biases and how they impact decisions. Next, we have a talk that looks at forecasting, a case study of machine learning and forecasting. And finally, we'll look at a quantitative method to bridge between the disciplines of data science and decision analysis. Our goal here is to help decision analysis, decision analysts better work with and derive value from the valuable insights that data scientists and their machine learning methods provide to their projects. I'll now hand it off to Chelsea, who will introduce each of our speakers.
Thanks so much, Neil. My name is Chelsea Maximovich, and I'm your co-chair for this session. And I'm delighted to introduce our first speaker, Fabrizio Dell'Acqua. Fabrizio is a PhD student at Columbia University's Business School, and his research focuses on the role of artificial intelligence in the workplace. In particular, he has been working on how firms should design human and AI collaboration to make it more effective and inclusive. While much work has focused on understanding the tasks where AI outperforms humans, Fabrizio studies whether and how the augmentation of human capabilities allows teams of human workers and AI to perform better than AI only. He holds master's degrees in economics from Bocconi University and the London Business School and has co-founded multiple tech ventures. Please join me in welcoming Fabrizio Dell'Acqua.
Thank you, Chelsea, for the introduction. Thank you for the invitation. My name is Fabrizio Dell'Acqua, and today I'm presenting joint work with Bo Cowgill and colleagues at the Computer Science Department titled Biased Programmers or Biased Data, a field experiment in operationalizing AI ethics. So the topic of AI ethics has become more and more prominent in recent years. This an example, an article from ProPublica discussing how the software that is used to predict future criminals is biased against Blacks. This is another example about an hiring algorithm used by Amazon that allegedly it started discriminating against women. There are also some more positive takes and some discussion around how AI can actually help diversify and make better decisions, for example, in the startup pool. So there has been a lot of research on this topic, of course. Many different conferences were created around this issue. But this research and this discussion has been mostly within computer science theory. What we think is missing are empirical papers about the AI development process and its links to biased outcomes. In fact, of course, most code in production is not written by computer science theorists. And what we want to understand more are the organizational, the empirical, the behavioral aspects of algorithmic production. So how exactly is going on within organizations when they develop algorithms, and how we do end up with these issues in AI ethics. And so we can start answering questions such as, why does algorithmic bias arise in the first place, and also what in practice works to reduce algorithmic bias. With this paper, we take a first step in this direction. We run an analysis on 8.2 million algorithmic predictions of math skills that were developed by about 400 AI engineers. These 400 engineers were randomly assigned to different experimental conditions, and the treatments they were assigned to altered their incentives. Crucially, they altered the training data they received, and also we altered the awareness and the technical knowledge of AI ethics that was available to the engineers. We are going to analyze specifically two sets of hypotheses. The first one is labeled bias programmers, and it's the idea that the programmers themselves, the programmers developing the algorithms, have their own biases, which then are inputted into the algorithms. The quote here says, tackling the challenges of bias within technical system requires addressing workforce diversity. Of course, this idea is related to productivity, to diversity. It doesn't need to be necessarily deliberate bias, but it could just be implicit bias. And in our paper, we address this by having a diverse set of participants, about 30% are women, by performing an implicit association test, so a psychological test to measure implicit bias in our subjects, and by intervening experimentally with some bias reminders, non-technical bias reminders. Another set of hypotheses refers to bias data, and it's the idea that the data that we feed into the algorithm is biased. The quote here says, algorithms aren't biased, we are. Algorithms are mirrors. They reflect our biases. These biases get baked into machine learning projects through training data. And so in this perspective, bias is a technical engineering problem. And of course, there are several versions, but the idea is that firms use convenience data, and that is at the root of algorithmic bias. In our paper, we're going to address this with an intervention on better training data. In fact, some engineers received a convenience sample, and some received a properly weighted sample. And we'll address it with some technical training onto the engineers. Then we are going to ask the engineers to make predictions, and we are going to assess their predictions out of sample. We have ground truth math performance for 20,000 observations out of sample. And additionally, we randomized, we manipulated randomly the algorithmic inputs that the engineers got, specifically around gender. So some of the observations were randomly flipped in their gender or in their gender correlates for some of the engineers in our sample. And so this overall allows us to attribute the creation of bias code back to these issues in behaviors, in personnel, in management, on the machine learning engineers, and connect it to topics of incentives, training, effort, and attention for these machine learning engineers. And also to the worker characteristics. So we have a rich data set of programmer covariates, we have their education, their attitudes. Importantly, we have their demographics, and so we're able to assess that set of theories as well. And again, this would allow us to understand more about why do biased algorithms arise in the first place, and also what interventions are effective in eliminating them. We decided to focus on accuracy because even if decision makers have additional objectives, so for example, a decision maker might have an explicit preference for diversity, still having unbiased prediction of ability would put them on the efficient frontier. And so we ask our engineers to be as accurate as possible and to focus on accuracy. And in general, engineers by themselves would not typically formulate alternative criteria. Now, I'll go through the empirical details and then present you the results. So as training data, we use the OECD PAX dataset. This administrative data is collected by the statistical group at the OECD for representativeness. It's a canonical data set used for cross-country comparisons of math literacy. So if you've seen a ranking of different countries on math ability, they probably use this data. Unfortunately, it doesn't have very detailed data about ethnicity. So for this study, we're mostly focusing on gender disparities. And the subjects in the data, they were tested with on a math ability test. And this is a type of a skill test that an employer might use to screen workers. So it's somewhat comparable to standardized testing. And additionally, we have more than 5,000 covariates per person. And we told the AI engineers they could use whatever method they wanted to work with this data set. Some engineers received a random training sample from our data set. So a random training sample of the whole data set that we had. Instead, some others received a sample featuring realistic sample selection bias. And what is realistic sample selection bias in this context? We gave them a data set that included only people that were already doing math-related jobs. So this resembles a problem that is faced by many real companies when they have to create a hiring algorithm, for example. They have data only about the people they have already hired. So that's how we created a sample that was selected. And it was selected among people who were already doing math-related jobs. And I'll now describe the experimental conditions in greater detail. But first, just a question, why math? Of course, math is very important for many high-wage careers. It's important in business, engineering, and so on. But also, it's a topic of important gender stereotypes and self-stereotypes that may lead to algorithmic bias. And of course, progress in this area may help alleviate persistent disparities in these math-heavy areas. Also, importantly, we have objectively correct answers, so we can actually compare subjects' algorithms against ground truth. So we know how our subjects performed on a math test, and then we ask the engineers to make predictions. As I told you, the subject population that we use were about 400 engineers. They're not told they're in a study. In fact, they are asked to help a company develop a resume screening algorithm. 80% of our subjects were recruited through an AI bootcamp at a major research university. They had on average 1.2 years of programming experience. 31% had already worked at a major company in a tech role, and about half were coming from industry, while the others came directly from either master or PhD. Then we had 20% of our sample, which we hired directly as freelance programmers. So they were slightly more experienced. They, on average, came from a bit less elite education. They had 4 years of programming experience around very, very similar tasks. So a lot of their tasks in the past involved creating algorithms for companies, and that's what we asked them to do. Our population is slightly more diverse than the software engineer population as a whole in the US. So we had 30% female as opposed to 22% in the software engineer population in the US. So to clarify a bit more, this is the ad that we used to recruit freelance engineers. It was a machine learning ad. We said, one of our client companies is interested in bringing analytics into hiring, and we asked them to develop a hiring algorithm. And this is the Bootcamp Overview. This was a machine learning course, and the participants to this bootcamp, as one of their assignments, they had to develop a hiring algorithm for this company. Now, onto the design. We had 4 groups. The first group received the bias training data, which is what I described earlier. So this training data that only included people that are already working in math-related jobs. The second group received exactly the same data, but in addition, they received a non-technical reminder. So just a few paragraphs that in plain English told them that this data might be biased and they should be careful. The third group received the same bias training data, the same non-technical reminder, and in addition, a jargon-free piece of technical advice on how to address sample selection in their data. Finally, a fourth group received actually unbiased training data. So this is the unbiased sample that I described before. And we ran a number of strategies to avoid contamination. So this is the text of the non-technical reminder. I'm not going through it all, but just to give you an idea, as a reminder, our recruiters' expectations about who to hire may have been systematically wrong. As you write your algorithm, please be mindful that your training data set may originate in a biased social system. Adjusting your algorithm to account for discrimination in hiring, self-sorting of applicants, or other sources of such bias could improve your accuracy. Now, what did we find? First, what we found on biased training data. So the biggest effect out of anything in this experiment came from the group who received less biased training data. So the group who received the unbiased sample of the whole data set that we had from DAAG, they performed best on performance and on bias. And they were by far the best group. Interestingly, about 1/3 of this benefit came, the 1/3 of the benefit from better training data came from a novel reason, that is effort. So engineers in this group spent 31% more time adjusting their algorithm, improving their algorithm. So a good chunk of the improvement came simply from the fact that they had better data. But about 1/3 of this improvement came from the fact that they simply spent more time. Once they had better data, they also worked on their algorithm more. So in our experiment, data and effort worked as complements. Then we look at discrimination, and we find that about 60% of our programmers directly utilize the gender variable in their algorithms. So remember that we flipped randomly gender, and gender correlates for some engineers. Nearly all programmers who use the gender variable favored men. And actually, they were more likely to use this gender variable if they were in the unbiased data group. So when they had better data, they were more likely to use every variable in the data set. They use this automated, unsupervised feature selection. And so they were closer to the so-called kitchen sink approach, rather than reading the code book and choosing and maybe being more mindful on what type of data they were using in their algorithms. Moving on to programmer characteristics, we found little evidence that minority, female, or less biased programmers wrote more socially aware code. So remember here, less bias meant that these programmers underwent a psychological test meant to elicit implicit bias. And so we found no evidence that that either minority engineers, female engineers, or engineers that were less biased according to this test wrote more socially aware code. And this was robust to different definitions of which programmers should be more socially aware. Interestingly, however, prediction errors were correlated within the programmers' demographic groups. So that means that the errors made by men, for example, were correlated with the errors made by other men, but uncorrelated with the errors made by women. So although their individual algorithms were not more precise on average, if we were to create a team, we might think that putting together engineers that are diverse might increase our accuracy and decrease our bias, because we aggregate more uncorrelated signals and we can reduce the error. And then finally, some practical solutions that we tested. We first looked at simple reminders about algorithmic bias, and these were very effective. They were almost half as effective at improving overall accuracy as receiving the unbiased data as training data. So this happened mostly through variance reduction, but this was a group that was receiving a biased training data set, and in addition, a simple reminder that this data might be especially biased. This was enough to improve their algorithm by almost half, as much as they would improve their algorithms with a better data. Instead, the engineers that received technical advice actually made their outcomes worse. So these engineers received both the non-technical reminder and also 3 pages of a technical reminder outlining how to address sample selection. And what we find is that a subset of the engineers actually improved their algorithms and was able to use the technical advice well, but a majority of the engineers in these conditions spent a lot of time trying to implement this advice, and they did not actually manage to implement it well and to improve their algorithms. And by spending this amount of time into trying to use the technical advice, they actually made their algorithms worse. So in conclusion, of course, most algorithmic fairness literature is in computer science theory, but most code in production is not written by computer science theorists. So with this experiment, we address this gap, and we focus on code that might be written by employees in organizations who are subject to pressures that are typically not those considered in computer science theories. And we did so with a field experiment on about 400 AI engineers. And to come back to the title question, the idea of testing biased programmers and biased data, what we find in this study is that although both are issues of representations, biased data had the biggest impact for the outcomes that we measured. And these specifically came through complementarities between data and effort. So engineers who received better data also exerted more effort, and they were more susceptible to incentives. Then we found that the benefits from a diverse set of programmers, so the benefits of programmer diversities, were coming from uncorrelated errors. So in particular, if we look at the errors of men, these were different from the errors of women on average, but similar to the errors of other men. And this suggests a way to create better teams of AI engineers. Thank you.
Our second speaker this afternoon is Dr. Xiaojia Gua, who is an assistant professor of decision and operations in the Robert H. Smith School of Business at the University of Maryland, College Park. Prior to joining the school, Dr. Gua completed her PhD in management science and operations at the UCL School of Management, University College London. Xiaojia's research and teaching interests focus on predictive analytics and data-driven operations. Her work spans applications in project management, demand forecasting, healthcare, and aviation management. Xiaojia has also received various accolades for her research. Most recently, she was the winner of the Informs Decision Analysis Society Best Student Paper in 2018. She was a finalist of the M&SOM Practice-Based Research Competition and the POMSJD.com Best Data-Driven Research Paper Competition and the Daniel H. Wagner Prize for Excellence in Operations Research Practice in 2019. Please join me in welcoming Dr. Gua.
Well, thank you, Chelsea, for the great introduction, and I'm very happy to be here and share my work. So today I'm going to present our work on machine learning forecasting project delays as an input to decision making. So specifically, I'll talk about our work on analyzing project schedules and predict project delays by contextualizing each task in a project using the text information of the task itself and its surrounding tasks information. And this is joint work with Professor Yakush Kane from Darden, Virginia, and Professor Bert Direct from UCL School of Management. So we all know that project fails everywhere. And forecasting project durations and costs accurately is very difficult. So maybe you won't be totally surprised when you see the following headline about some major projects in the world. So this was right before the World Cup in Brazil. The stadium wasn't going to open on time. It was completed 4 months behind schedule, and there was huge cost overrun. And this is a major infrastructure project in the UK. You may have heard about this. So the high-speed train from London to Birmingham is also in trouble. So the start of the project was first delayed to March 2018 and then to December last year. So this is not even the project itself. It is the start date of the project has been delayed several times. And the high speed to chairman stepped down and the cost of the project is out of control. So is this just an issue with public funded project? Well, no. Here is a headline from 2018. So Apple canceled their projects after numerous delays and failed to accomplish of what they hoped to accomplish. So projects delay and fail all the time. And our research project is all about, can we improve project planning? Can we better forecast the project delays using machine learning and data? We only studied project delays here, but the method can be easily generalized to predict the cost overruns. So let me tell you a little bit more about project's performance. So this is a study conducted in 2018 by the largest project management institution in the world. So they reported on performance of the major projects in the world. Here we have the performance of projects that met original goals, completed within budget, and the green line shows projects that were completed on time. So overall in this figure from 2011 to 2018, there aren't that many changes in the green line. So the percentage of projects completed on time is around 50% all the time, meaning not much improvement, not much change in any way, even though people have been investing in project management tools since 1960s or 70s. So there's little progress, yet the problem is huge. So how big is the problem and why do we need to care about project performance? We care about project performance because a lot of money have been invested in projects. These are some statistics and we can have a look at these numbers. So GDP contributions from project-oriented industries, the companies that run projects on a regular basis, that can be new product development, technology, construction. So the GDP contributions are $20 trillion. And around 10% is wasted due to poor performance. Then there's about $2 trillion wasted every year for per project performance. So why is it so problematic? Why is planning so hard? Well, it's actually really hard to predict in advance how long it will take, how much it will cost. First of all, the structure of projects is usually complicated. A project often consists of several individual tasks, and these tasks are all linked together. For example, in this project here, if we don't finish task G, we can't start task KLM. And KLM are also linked to some other tasks. So this is the classical project management tool you may be familiar with. A manager can input task names, dependencies between tasks, and estimated durations. Then the tool will create a Gantt chart and calculate how much time the project will take. These tools are very internal looking. Their results based only on a manager's estimates of individual tasks in this single project. They don't give us any concept of what happened in similar projects elsewhere. So in our study, we want to take an external view of the projects and see if using historical data of plans and actuals, can machine learning help predict the delay of tasks? We collaborate with Nplan, a construction project management company in the UK, and collected over 250,000 construction project plans and actual timelines in the UK and Europe. When we look at these complicated schedule files, we realize actually there's a lot of useful text information in these files. For example, task names often describe what this task will do and what would be a key factor affecting the delay of the task. So in this project, we try to develop an approach using machine learning and AI techniques to learn the context of a task by incorporating the structure of the project around this task and some text information of the task. Then we want to test if this approach can help predict task delays. So natural language processing has been applied in some business studies, operations, marketing literature, but this literature mainly focuses on sentiment analysis. For example, mining customer reviews on Yelp and see the impact of sentiment extracted from these reviews on the survival of restaurants. Sentiment analysis is very convenient, but it won't be helpful in our case because there's not much sentiment in project names or description. Our goal is to use this text as predictors in a predictive model, and predictive models don't take text as input. So we first need to transform this text to numeric representation. In computer science studies, researchers have developed methods to transform words to a vector of numeric values. These studies usually focus on predicting the next few words in a sentence. For example, right now, Gmail has a feature to help you finish your sentence, and it's actually pretty accurate. However, there are very few studies have tested the predictive power of these numeric representations and how should they interact with other variables or predictors in your model. And this is a already ongoing experiment with several companies in the UK and Europe to try to implement this framework. We already have collected tens of thousands of plans, detailed plans with actuals. We create a database of project tasks. We use natural language processing to learn from the text information such as the name, description of the task, the description of the work breakdown structure to build a corpus or like a language source for project planning. So this could be a contribution from our project because right now the widely used corpus are mainly based on news articles or tweets. I'll explain this in detail in the next slide. Then we use natural language processing to get numeric representations. We develop predictive models to apply these representations and some other variables to predict task delays. Hopefully, we can also determine key factors that impact the project delays. And finally, we wanted to study the delay and uncertainty of the entire project based on the predictions of individual task delays. So to encode text data into quantitative format, we apply a method called word2vec. It is a pretty widely used approach to finding numeric representations of word or sentences. So the idea is actually quite intuitive and easy to understand. The model is based on a two-layer neural network, which takes in some input data, then the hidden layer applies some functions to the input data and eventually generates some predictions as output. In a word2vec model, the neural network takes a large amount of text information, like millions of news articles or tweets posted online, and then try to learn the meaning of each word. Specifically, the neural network is trained to predict the surrounding context or surrounding words based on a given word. For example, suppose there is a sentence, high-speed train means major rethinking. And then the model will first take speed as an input, then predict high and real, and then take the real as input, then predict the speed and ease. And eventually, after training the model, the algorithm takes the intermediate results here, the numeric results in the hidden layer to represent each word. So we use this technique to train our word2vec model using the names and descriptions of tasks in the 250,000 projects collected with the company empty plan. So this model is tailored for construction projects. It's built to understand the context, the meaning of words in project management environment. So when you input data to this model, it will return a vector of 50 numeric numbers to represent the word. And each numeric value represents like a dimension of the word. An individual dimension means nothing. But then the 50 numeric numbers as a vector collectively represent a word. Okay, now using the word2vec model, we have a numeric representation of task names. Here are some other features that we consider as predictors in predicting task delays. number of predecessors, number of successors, and number of parallel tasks. Suppose we are trying to predict this gray task in the project, then the number of predecessors is 6, because these 6 tasks are linked directly to this gray task. And then the number of successors is 2. Number of parallel tasks is also 2. So these 3 variables can basically describe the complexity of the project during this period. This might be important because, for example, if there are a lot of parallel tasks, the project may lose focus and cause delays. So we also consider relative position, which is defined as time since the project's start divided by total duration of the project. And in this example, the relative position of the gray task is 120 divided by 150. So I think this variable could measure the location of the task in the project. Does it happen at the beginning of the project, or it happens close to the end of the project? We also consider planned duration as a predictor. And finally, the target variable in our model, the quantity that we are trying to predict, is defined as the task delay, which is equal to actual duration divided by planned duration. So we tested several models on 2 like toy data sets. The first data set is a public data set collected by researchers at the University of Ghent. It has different kinds of projects, from design questionnaires to build like patient transport system. And the second data set is the construction project schedules provided by Implant. We picked up 72 projects and over 7,000 tasks. So these 72 projects are guaranteed to be clean. And we use a small data set now just to speed up training and testing of the predictive model. Eventually, we will, of course, scale up the test on the entire data set. And as you can see from these summary statistics, the projects in the second data set are more complicated with more number of tasks, longer durations, and with more severe delays. So here are some accuracy results in predicting task delays using a simple regression tree model and the data from the first data set. The data were split into a training set and testing set. We fit the model in the training set and generate forecasts in the testing set. We try to use simple regression tree model because it's intuitive and we can better understand the impact of the predictors as a first step. So the aim of the current empirical evaluation is to see if text information or the name of tasks can help predict the task delays. So we tested the model with and without text information. In the first model, we fit a regression tree with all the variables except the task names. And this model has a mean absolute error of 0.473 in the test set. And based on this model, the most important features are relative position, number of predecessors, and planned duration. In the second model, we fit the regression tree with only text information, so the name of the task. Remember that each task name is represented as a vector of 50 numeric values. So there are 50 predictors in this model. And this is how the training data looks like. The mean absolute error of this model is 0.554, much higher than that of the first model. So it may not be a good idea to use only task names as predictors. What you're doing in this task is important, but other information about, for example, the planned duration or the tasks around this specific task are also important. Okay, now we have 2 separate models. What if we put all the predictors together? Text information, number of parallel tasks, everything together. So the accuracy of this model is slightly better than the regression tree without name of the tasks, 0.470 versus 0.473. But if we look at the regression tree, we can see that actually different columns in the task name matrix interact with different predictors, which means each column in the task name matrix is considered as an independent predictor. However, as I mentioned before, the vector of 50 numeric values collectively describe task names. So we may expect them to stay together in the tree as a whole part that represents the effect of task names. So eventually we go into the algorithm of the regression tree, we add some constraints to the tree. So if any numeric representation of task names are going to appear in the tree, they need to appear together as a whole part. And the accuracy of this tree model has significantly improved from 0.470 to 0.375. Based on this tree with constraint, we can see that task name only appears on the left-hand side. Since the root node is relative position, therefore, task name is an important factor only when this task takes place at the first 75% of the project timeline. When the task is pretty further down the timeline, it doesn't matter what you are trying to do in this task. Number of predecessors, number of parallel tasks, those factors play important roles. And according to this tree, if we look at the branch that leads to the bucket with the highest delays, we can conclude that the task with most severe delays often start during the last 25% of the project timeline. When a task is further down the timeline, there might be more uncertainties, more likely to run out of resource, which could cause delays. And these tasks usually have more than one predecessor and more than two parallel tasks. If the task doesn't even have a predecessor or parallel task, the project is relatively simple during this period, and the team can really focus on this task to make sure it won't be delayed. So these are some insights summarized from the regression tree. And here are the results for dataset 2, the results for the construction projects. Basically, the results are very similar. The regression tree with constraint of putting all the numeric representations of task names together achieved the best mean absolute error. So these initial results show that including text information could help predict task delays, could make the model more accurate. Right now, we only consider task name as predictors. But as I mentioned before, our ultimate goal is to contextualize tasks by also incorporating its predecessors, successors, and parallel tasks text information. However, how to incorporate information of tasks around the target task is not trivial. Every task has different number of predecessors, successors, parallel tasks, which means each task has different number of predictors. To train a predictive model, the observations in the data set need to have same number of predictors. So we need to find another way to quantify their effects. And right now we have a very initial idea of how to quantify the effect. So here is our current approach. We first put task names through the word-to-vec model trained using the construction projects, and then get the numeric representations. Then we use these numeric representations together with other variables as input to a predictive model. Okay, but now we are trying to add another step after getting the numeric representation of the tasks. The graph convolutional network has been applied to study social networks, and we realized that it can also be applied to describe the structure of a project. So the input to this model has two components, a feature description of task names, etc., and several metrics that describe the structure of the graph or project. So the output of this model will be task delays. So this approach could provide more accurate forecasts, but it will be very difficult to get any intuitive results. And it also requires a large data set to train the model. Right now, we are still testing on this model and see if it can improve accuracy. So here I've listed some future work in our study. As I mentioned before, we'll further contextualize the tasks by incorporating predecessors and the successors text information using the graph models. And then we'll also scale up the numeric evaluation using the 250,000 construction projects. And finally, we also want to predict the distributions of task delays and the whole project delays. So right now, we only focus on point estimates, but we are actually also interested in the distributions of task delays and the whole project delays. So I'll just stop here at this list of future work. So this is everything I'd like to share with you about this project today. Thank you very much for listening, and I'm happy to take any questions you have on this study.
For our third speaker for this session, we're going to go to Dr. Neil Hamlet, a strategic data scientist with experience spanning multiple industries. Neil Hamlet is a thought leader on how information and decision-making contribute to competitive differentiation. A senior data scientist at International Consulting Associates, Dr. Hamlet helps the U.S. Food and Drug Administration's Office of Clinical Evidence and Analysis with analytics-driven information of its regulatory functions. His multi-decade career includes tenures with IBM and as a U.S. Navy engineering duty officer. He holds a Doctor of Science from the George Washington University and a Master's of Business Administration from the McDonough School of Business at Georgetown University. In addition to the Society of Decision Professionals, Dr. Hamlet contributes to the American Statistical Association, the Institute for Operations Research and Management Science, and the Strategic Management Society. Today, Dr. Hamlet will bring all of the sessions together, and he'll describe an approach to bridging data and decision sciences. He begins by considering how practitioners in their respective disciplines think. They come from different branches of the probability and statistics family tree. This motivates a quantitative approach to making machine learning methods more directly useful in decision analysis. The advent of the meta-log distributions further provides opportunities to make machine learning results more informative for the decision quality framework. Please join me in welcoming Dr. Neil Hamlet.
Thank you, Chelsea. Data science, machine learning, and artificial intelligence, terms that I'll use interchangeably here, have attracted a great deal of attention in the decision analysis community during the last couple of years. DAAG and local chapters have offered data science workshops. These have tended to resemble data science indoctrinations. Here, I want instead to describe how data scientists think. I'm speaking more to decision analysts than to data scientists. I'll then show a quantitative approach using meta-log distributions. I ask you, however, to focus throughout on our approach to reasoning rather on the mechanics of calculation. So let's begin with the decision quality framework. Many SDP members are intimately familiar with this approach. This is the position from which we should begin with thinking about how to incorporate machine learning into decision making. Let's assume the following premise going forward. AI and decision analysis are complementary. One is not a replacement for the other. Fabrizio talked about how biases show up in AI algorithms. DQ, of course, devotes a great deal of time to the study of biases and how they influence decision-making and how to mitigate them. Xiaoxia's case study shows how machine learning predictions fail to perfectly explain variations and outcomes. DQ is explicitly designed to deal with these types of uncertainties. Now, data science and decision analysis, as we said, are complementary disciplines. They are, however, divided by a common probability and statistics language. Data science and machine learning have their roots in classical statistics. Their focus there is on establishing hypotheses regarding which we can assert a certain degree of certainty. The p-values and statistics are an example. When p-values meet certain conditions, the statistician is going to say that we are effectively certain about a particular hypothesis. Decision analysts look on the opposite side of the same coin. They're interested in the degree of uncertainty regarding the factors of the decision. This is often represented using probability distributions. DA practice has in the past used devices such as probability wheels for this purpose. What probability is, how it's thought of, is one of the root contributors for this division. The true professions come from different branches of the probability and statistics family tree. Data scientists tend to think of things through a frequentist prism. DAs tend to be Bayesian. As our quote from Lawrence Savage here indicates, these positions are not intractable. With some work, we can bring them into alignment. And that's what we want to focus on here. Now, I offer here 4 axioms on thinking about machine learning in the context of decision analysis. And these come from a variety of sources. The first one from a Harvard Business Review article a couple of years ago says that it's math, not magic. There's a lot of hype underlying AI, but at the end of the day, it's mathematics. One of my favorites is from Stephen Hawking. Calculation is to mathematics what typing is to writing. Now, what is beyond calculation and math? This third axiom says that probability is not really about numbers, it's about the structure of reasoning. So it's about the thinking and the logic at least as much as it is about calculation. Finally, back to Lawrence Savage, the purpose of statistics generally is to discuss the implications of statistics to making decisions. And what is the punchline here? Machine learning provides statistical evidence for decision making. As we get to the end of this discussion, we'll circle back to the DQ framework and think a little bit more closely about how statistical evidence weighs into decision quality framework. Now, what I discussed, the idea that data science, machine learning, and decision analysis looks different, motivates thinking about approaches, computational approaches that bridge between these different schools of thought. This diagram here represents an approach on how to make this happen. I ask you not to be overwhelmed by the complexity. We will walk through this block by block. This is under development. There will be my ambition is to have a Python library available for practitioners later this year, hopefully around the time of the joint statistical meeting. And finally, I want to call attention to the importance of metalog distributions. This is if you haven't seen Tom Keelan's presentation on metalogs, I encourage you to go back to that and watch the replay. Metalogs are one of the most important innovations that's happened in the statistical sciences in the last few years. Finally, as we walk through this, please focus not on the approach to calculation, but focus on this reasoning, the way we think about this, the logic. So now here's the first step. This is where machine learning practitioners such as Xiaojia live. They focus on fitting statistical data, fitting statistical models to explanatory data. And in the case here, which is a different case, slightly different from the type of problem Xiaojia described, this is a regression model or an estimator. What we're interested here is in residual analysis. Machine learning practitioners don't generally perform residual analysis as more conventional statisticians do, but that's our way ahead. Machine learning practitioners will typically compare your observations with your estimates and give you point statistics about how well the model explains the data, but that's not informative to the decision analysis methods. Decision analysis looks again at probability distributions, and our motivation here is to look at how we can get from residuals to probability distributions. Now this plot here, this is a residual plot, which is a mechanism for looking at the residual error or the unexplained variation in a model. We usually look at this with in conjunction with a response model, which compares the observation and the estimate. I'm not doing that here for purposes of time. This data is incidentally from a widely used Kaggle challenge. It's not trivial, but it's not overwhelmingly complex. And it's sufficiently complex to exercise our mechanisms here. Now, we're interested here in turning this into a probability distribution. And that's where our next step comes in. Now, machine learning practitioners will look at the types of variance they look at in their results include a bias and what they call variance. Bias, which we'll focus on here, is the extent to which the model doesn't capture the underlying structure of the data. Some practitioners use a concept called locally weighted scatter plot smoothing to look at bias. It's a nice, obvious visual approach. The key observation here is that bias resembles a particular type of machine learning model called a k-neighbors regression model. And this is basically, it's a way to scan through our residual plot that we looked at before and understand what's happening locally in our distribution. So to this, I've added both the lowest plot, which is the indication of the bias, and the k-neighbor regression model. My goal here is to test the hypothesis that the k-neighbors is approximately represents the lowest model. These incidentally are commonly available packages both in R and Python. So quantitative practitioners can lay their hands on these easily. So there are two key observations here. One, incidental to understanding the data, this model has some bias in our results. We see that because the lowest curve, the yellow-colored lowest curve diverts from the red-colored zero bias curve. The second observation, which is incidental to our computational approach, is that the k-neighbor regression is approximately resembles the lowest. It's not quite as smooth, but it roughly tracks it. This this is basically the motivation for the overall computational approach we described before. Now, here's the final step. This is where we bring in the meta-log distribution. What we want to do is we want to scan through our residual analysis and take vertical slices in the distribution before, and we want to fit meta-log distributions to them. As a result, we get a probability distributions of the type decision analysts and operation analysts are interested in. And we use our K-neighbors algorithm to figure out how to slice and scan across the distributions. So this illustrates the type of result. And we see here that fitting, what we've done here is we've scanned across the distribution, and we have fit the meta-log to vertical slices, which are vertical neighborhoods of estimates in our scatter plot, in our residual plot here. And this gives us contour lines. The really interesting thing here is this opens up the opportunity to bring statistical inference into machine learning practice in terms of bridging between decision analysis and machine learning. We can, instead of getting point statistics, we can end up with distributions for which we can calculate conditional probabilities. For a scenario analysis, our different scenarios might be distinct models, each with its own residuals and distributions based upon meta-log fits, or they might be distinct models with similar distinct distributions. Now, to wrap things up, I want to bring it back out of the technical details back into the decision quality framework. This is a representation, this is an attempt to represent how decision quality and machine learning influence the links in the appropriate, in the decision quality framework. And the point here, the big idea is that machine learning provides statistical evidence for decision making. The decision quality framework still rules. We have machine learning and artificial intelligence, however, as new sources of information. And we see for each of the links how the directionality of the influence from D, Q, and I interact with each other. So the framing shapes and guides the activities by the data scientist on the team. Decision quality, one of the key aspects, it's about identifying creative alternatives, and modeling and simulation help clarify these alternatives. They can provide quantitative structure. The key focus here we see today is that machine learning can provide new insights, and the use of meta-logs to provide probability distributions and the types of information that Xiaojia provided are sources of information that address that relevant and reliable link. Key values and trade-offs is key. Key values and trade-offs, clear values and trade-offs emphasizes filtering out the bias. We see from Fabrizio that biases show up in machine learning and artificial intelligence. The results shouldn't be taken at face value. They should be evaluated and cross-examined. Xiaoxia's example, her case study shows how quantitative methods can provide rigor, quantitative rigor to aid with the sound reasoning. And finally, the methods interact each other throughout a project as part of the commitment to action link. So again, these two disciplines are complementary, and skillful alignment of them can make decision analysis and decision quality much more powerful. Thank you for your attention, and I look forward to questions and dialogues in the breakout room later.
All right, hello everybody. And now we have some time for some questions. I'm going to start things off with a question for our entire panel. And I'd like to start with Fabrizio, but I'd like to know, or I think our DAAG community would like to know, what are the biggest challenges to getting data scientists aligned to a decision quality framework?
Yeah, thank you, Chelsea. I think so. As Neil discussed, machine learning would provide statistical evidence for decision making, and it wouldn't influence decision quality directly. I think what comes out of our study is that this value aspect should be taken into account, and should be taken into account when asking the machine learning question and when having machine learning influence decisions. So aspects such as how to build the teams that create the algorithms, what underlying data is going to be used, and even more behavioral, possibly organizational, team-specific aspects on how engineers are asked the question, how do they frame the problem. These may have very relevant consequences and affect decision quality down the road.
All right, thanks for that great answer. And the same question to Xiaojia. What are the biggest challenges in your experiences of getting data scientists aligned to a decision quality framework?
So I think in my opinion, data science has been developed faster than like new decision analysis algorithm or tools. So I feel like there's kind of there's a group of people who only focus on data science, like I generate better predictions or I come up with better intuitions through experiments. And then there's another group of people, they use very simple forecasting results or very simple intuitions from some experiments and make decisions. So I feel like there's some kind of misconnection between these two different fields. For example, my research area is more on forecasting, and we always talk about forecasting accuracy, and we are very excited when we can improve the accuracy by 1% or 2%. But actually that may mean nothing to decision making. And sometimes you get different forecasts, but actually those forecasts will lead to the same decision in the end. So I think in my opinion, there should be some studies take both data science and decision making process into consideration. Like there shouldn't be a group of people only focus on one aspect of these two areas. Yeah, so that's my little bit input to this question.
Thank you, Xiaojia. And Neil, your answer to the same question.
Generalizing is probably risky here, but we can talk about a couple of facets of this. The first one is how data science and artificial intelligence are viewed. There's many people who look for input from data scientists are basically might assume that the calculation is a substitute for the decision. as opposed to the statistical calculation as evidence to support a decision. So it's how data science and AI are employed in practical contexts. The data scientists are not often exposed to a decision quality methodology. On a more practical basis, data scientists, again, tend to be frequentists and might be blind to the sorts of cognitive biases that lead to conclusion biases of the sort that Fabrizio described.
Great, thanks for that, Neil. I have a quite specific question for Xiaojia that's come in. And the question, it's a two-part question. Does the model predict the actual to original plan duration ratio? And did you attempt a classifier dependent variable, so late versus on time, where late is defined as completing the project before a certain percentage from the original plan?
Thank you for the question. So in terms of the first question, yes, the model actually predicts the ratio as the question just described, is the ratio of the actual to the planned duration. And then for the second question, I think that's a good idea, but we are not doing it in this project. Actually, in practice, N-Plan, the company we worked with, they divided delays into like different buckets, like delay 0% to 2%, 2% to 3%, 3% to 5%, etc., and fit a classification model. I think it would be fine if we only focus on task delays. But for us, however, we are also interested in the delays of the entire project. And in this case, the actual delays or durations are very important. So we can't just do a classification model. We need to know the actual duration or the actual delays, because later we can run simulations and then calculate the duration of the entire project. Yeah, thank you.
All right, thank you, Xiaojia. And now a question for Fabrizio. You mentioned that all groups produce bias and that some produce more. Now, how big are these biases? The most, least, average, standard deviation? And how much did these values change with the different experimental treatments?
Yeah, thank you. Thank you for the question. So the mean average error for the average programmer was 0.77 standard deviations. And so this is in terms of accuracy. We have a few ways of measuring bias. So that's, yeah, I don't remember the exact number on that, but these results were in line. And with the best treatment, so by giving them the most accurate data, they reduced on average their error by 0.21 standard deviations. So this is the best benchmark. And then things like the reminder worked about 50% as well as giving good data to the programmers in improving accuracy and reducing bias, while the technical advice had about the same effect in the other direction. So it increased error by that amount.
Fabrizio, we also had a question further to that on the reminder about that the data could be biased. And can you comment on why that reminder worked so well? And how can this be applied beyond this context? Because you've spoken a bit about the diversity and equity, some of these critical intersections, like for example, with gender. And maybe can you talk a little bit about that particular influence and where it could be used elsewhere?
Sure. Yeah. Thank you. I think that's super interesting. That's something we are exploring right now. So one thing to notice is that the data description for the group that received biased data and the group that received biased data plus a reminder was exactly the same. So technically speaking, the group that was reminded of potential bias in the data did not receive additional information. And the other group could have understood as well as the reminder group what data they were working with and where the data was coming from, what were the selection problems. However, when we ran a survey after the task, it turned out that the group that read this non-technical reminder was actually more aware of the potential bias. So a very light intervention, something like a nudge in the behavioral economics literature, turned out to be quite effective in this specific case, simply by making engineers more aware of some of these issues that we discussed and that also Neil mentioned before. So there seems to be some sort of saliency effect. These potential biases became more salient for the engineers, and this led them to produce more accurate and less biased algorithms.
Thanks, Fabrizio. A question to Neil now. Can you talk a little more about your plans for applying the metalog distributions to predictive model residual analysis?
Yeah, thank you for that. So the goal, it's picking up on things that Michael Lieberman referred to yesterday in his talk, and Ed Rogers alluded it too. It's the motivation here is a more thorough characterization of uncertainty associated with data science and machine learning techniques. There's a formal framework within the machine learning community called the bias variance decomposition. It's a little bit like analysis of variance in classical statistics, but it's treated in primarily as a heuristic in data science training programs by which to look for overfitting. Where I want to take this is the first step is to explicitly calculate terms in the bias variance decomposition. Metalogs give us a tool to do that, and that will provide us with a more complete way of characterizing the uncertainty, different types of uncertainty resulting from machine learning results.
Thank you, Neil. So I'm going to come right back to Fabrizio. I've had a very interesting follow-up question to what you were just talking about, and I want to come to it before we lose this great conversation. So for Fabrizio, regarding biased data leading to biased models, is this a problem, a more modern reinstatement of the statistical problem of drawing inferences from bias samples? And for machine learning enthusiasts and practitioners, could better statistical education, particularly on how to apply good sampling to generate training data, would that help?
Yeah, thank you. Yeah, I really like this question. I think, so for the first part, definitely that is a more modern restatement of that problem, and that is a problem that we're carrying even with this more modern machine learning methods. So we need to be mindful of that. But regarding the point about education, this was exactly our prior before launching the experiment. So we thought that better statistical education could have helped, and we still think in general might help, but this was the point of implementing a technical advice group. So one of the randomly assigned treatments received technical advice, and this is precisely this idea of giving them better statistical education in a sense, even simple ways like reweighting their sample. So, but what happened is that about 20% of the programmers in this group improved on the results of the other group. So for them, the technical advice actually had a positive effect, but 80% did actually quite a bit worse. So the average treatment effect was negative, as I mentioned. And And notice also that this group receiving this technical education, this more statistical education, also received the non-technical reminder that I discussed before. So this nudging effect disappeared. There was no positive effect there anymore. And what happens is that a lot of the programmers in this group just spent a lot of time trying to implement these technical solutions, and many of them were not able to do so properly. So they, in a way, wasted some of their allocated time to the task, and did not improve their algorithms that way. While people in the other groups, without receiving this technical education, approached the problem as best as they could with methods they already knew, and on average they perform better. So definitely, I would say technical education still matters in my view, but one would need to be very careful in the type of tech advice that one gives, and also be mindful of the level, of the technical level of the programmers that are receiving the advice. And this is a mistake that we often see in the computer science literature, where these tests are made on very, very qualified samples, but then we found these behavioral reactions that we think should be taken into account in a practical context.
All right, thanks, Sean, for a really great question, and to Fabrizio for a very interesting response. Moving back to Xiaojia, question for you. Your current predictions are generated using a single regression tree. Why don't you apply those machine learning models with multiple trees, such as random forests?
Thank you. Thank you for this question. Random forest could be more accurate than a single regression tree. But as you may notice, right now we only fit the model to some toy data sets, very small data sets. So we may not need those more complex models. Also, I think a single regression tree could provide us better intuitions on how these predictors interact with each other, and why a task's delay is predicted in a certain manner. So I think it can help us understand the key factors that impact task delays. But eventually, when we scale up our test, when we use a large data set, we'll definitely try other methods such as random forest and see how much improvements we could get. That's my answer to this question.
Thanks for that. We are starting to come to the end of our time, and I have a couple of questions that have come in related to recommendations and best practices. So this is going to be a full panel approach, and I'm going to start with Fabrizio. But the question is, what are the main recommendations or perhaps best practices either to organize teams or decision makers? So you can think about it from both ends of that. What are the recommendations or best practices that you would suggest to limit AI bias, but also how can you make sure that data scientists are aligned to that data quality framework? So starting with Fabrizio, please.
Thank you. Broad question, big problem. I think, there's a few elements to this question. I think from the data science perspective, from the team perspective, there are a few suggestions coming out of our research. So definitely the first point would be to, if possible, improve your underlying data. So whatever this whole behavioral discussion and the team composition discussion that we've had, the main effect was still coming from data quality. So that remains fundamental. Once you've done that, focus on how the quality of data is communicated to the programmers working with the data. So this type of salience effect, these potential nudges are very relevant. There is a point about team composition. So I mentioned that we didn't find any differences in individual algorithms' accuracies, but there were the errors between different groups were uncorrelated, and they were correlated within groups such as men. So that might be suggestive of the idea that a more diverse team would improve your output. And then finally, this point that we discussed before about the technical advice. And so be very careful on the type of technical advice that that you give to the team and the programmers. From the decision maker point of view, so in terms of decision quality, once these inputs from machine learning are received, I would say the main takeaway would be to consider how the machine learning predictions were produced. So many of these issues might have been present. The data and the output is still very informative, but the way these predictions and these models were generated should be taken into account when making the decision.
Great, thanks so much for that, Fabrizio.
Thank you.
Xiaojia, your comments on this.
So I'm not an expert in this area. I feel like Fabrizio, you should be the right person to answer this question. But I'll just add my comment here. So first of all, I think the data quality is very important. Usually people who collect this data don't really need to work with this data. It's like they just collect this data and then pass this data to the programmer, to decision maker. So maybe get those programmer and decision maker involved at right the beginning of this process and ask for their advice or their requirement of the quality of the data would be a good idea. And also, I think maybe the education is also very important, like educate these people who collect this data, how should they, how would this data be used later and what should be the right quality of the data. And then also educate those decision makers and programmers, like how to better process this data and consider this bias when they think about algorithms and decision-making tools. Yeah, so this is my input in this question.
And over to Neil. Your brief answer will give you the last word here.
Yeah, so a couple of things real quick. One, the data scientist has to be part of a diverse team. The anti-pattern is to send the data scientists back in the closet to search for serendipity in the database. That doesn't work. The second is that data quality is essential. Third, I think that the natural pairing is between a data science and a decision analyst. The decision analyst is a critical interface who can help the data scientist frame the activities.
All right. Well, thank you so much to our speakers. That was truly fascinating. We so appreciate the time that you spent preparing for this conference and spending time with us. Just a reminder to the DAAG attendees, we now have breakout rooms with each of these folks. My sincere apologies if I didn't get to your question. You asked some great ones, but the good news is that if you didn't get a chance, your opportunity is now. So please join us in the breakout rooms.